All right, let's talk about graphs. 6 Degrees of Kevin Bacon. This is this fantastic game this is really from the days before IMDb, because now that there's IMDb, who really cares? You can just look this up. But back in the days, like in the 90s, you would have to look this up. Where you couldn't look this up. You would have to like have this mental catalog of who is in what movie. So you're like, can I connect Kevin Bacon and Carrie Fisher? Well, Kevin Bacon was in Flatliners with Julia Roberts, underrated movie from the early 90s. Julia Roberts was, of course, in Pretty Woman with Richard Gere, who was in Arthur, terrible movie from the 90s. A lot of movies from the 90s here. I wonder what the theme is. Anyway, we keep going and we get it in 5 links. And so this idea, like you could connect everyone to Kevin Bacon in 6 steps. And this 6 degrees goes back to, I think it was a research done in the 60s where, they were trying to figure out like everybody on Earth is like 6 links apart. Like there's nobody on Earth that you don't know somebody who knows somebody who knows somebody who knows somebody who knows that person or something like that. This link up here, by the way, the 6 degrees of Kevin Bacon, if you click on that, I don't know what happens if I click on that, so I'm not going to. But if you, I know what happens. It follows to the Wikipedia page, but I don't know what happens like in this recording situation because I'm using this new tool called Loom. Anyway, if you click that, it'll tell you about the origin of the game. It was invented by undergraduates at Albright College. Hoyt taught at Albright College for a year before we ended up here at Knox. Well, I was already here and she was still there. All right, moving on. We could do it differently to get Kevin Bacon and Carrie Fisher. We could go from Kevin Bacon to Tom Hanks to Dan Aykroyd, and then Dan Aykroyd to Carrie Fisher, because they were actually in Blues Brothers together. Believe it or not, Carrie Fisher was in Blues Brothers. Tom Hanks and Dan Aykroyd in the Dragnet movie. Interesting movie. It's one of these movies in the 80s where there's like a giant satanic cult with like dozens of members. Which I'm pretty sure that was never really a thing, but like it's part of the satanic panic of the 80s, which is kind of a weird and fun thing to read about for all of you millennials out there who are like, the 80s, that's my parents' generation or whatever. Moving on, graphs. Okay, so how do we represent this kind of thing? We'll represent it with a graph. So a graph is essentially a bunch of nodes or vertices with edges between them. So an actor is either a node or a vertex. And if 2 actors were in at least one movie together, we'll put an edge between them. And so you'll sometimes hear the term node, sometimes hear the term vertex. Math people tend to say vertex. CS people, especially if they come from a networking background like I do, tend to say node. So I say node all the time. I almost never say vertex unless I'm like specifically talking about, like in a very mathematical, like if I'm proving something, I might say vertex. Okay, I made this with GraphViz, but, this is just sort of an example, and I'm just using, like, first names for all of this, So, like, Kevin Bacon was Sarah Jessica Parker. They were actually, I think, in Footloose together in the 80s. Kevin Bacon's worked with Julia Roberts, who was in Pelican Brief with Denzel Washington, who was in... The hell was he in with Tom Hanks? I'm pretty sure this is Tom Hanks. Tom Hanks and Meg Ryan, of course, Sleepless in Seattle, and also You've Got Mail, 2 of the great romantic comedies, again, from the 90s. Julia Roberts and Richard Gere. I don't know why I'm telling you all of this. You can look all this up. Moving on. Graphs can be weighted or unweighted. So if we have unlabeled edges, this is just an unweighted graph. Now, in terms of an implementation, like if you have just a generic way to implement graphs, you're not going to really differentiate between weighted and unweighted. An unweighted graph, you just don't care about the weight. So you just make all the weights 1 or something like that. And that effectively makes it an unweighted graph. You don't, like if you have a weighted graph, you can use the same code to make the graph unweighted by just making all the weights 1 or making all the weights non-zero and just ignoring what they are. That'll work. Now, for our example with Hollywood, maybe we want to weight the edges with like the number of films the 2 actors appeared in together. That's a thing that you could maybe do. So, Tom Hanks and Meg Ryan, they'd have a weight of at least 2 because they've been in at least 2 romantic comedies together. Alec Guinness and Carrie Fisher would have a weight of at least 3 because they were in the 3 Star Wars movies together. Well, Alec Guinness wasn't really in Jedi very much, just like 1 or 2 scenes. Anyway, so that would be a potential way to weight this. There's also directed and undirected. So, if Kevin Bacon's in a film with Tom Hanks and Tom Hanks is in a film with Kevin Bacon, that's a symmetric relationship. So this is kind of like, in Facebook, if I'm your friend, then you're my friend. But some graphs are just sort of, they are one direction, not the other direction. So for example, Twitter's like this. So like I might follow Tom Brady, but Tom Brady's not going to follow Spacco. Like he's not going to follow me. That's just not a thing that's going to happen. Maybe I'll follow him to Tampa Bay. No, I'm just kidding. I'm not moving to Florida. It's going to be underwater soon. I'm just kidding. Florida won't really be underwater. It might. It won't. Okay, so if we were doing this for class, I would ask students to now come up with some examples. So, can you come up with another undirected, unweighted graph like Facebook? Another directed weighted graph like Twitter? Can you come up, directed unweighted? Could you come up with something that's directed and weighted and something undirected and weighted? Directed unweighted, that works for Twitter. Directed weighted? So that means there's an edge between things and we have a weight on that. I mean, I can think of some like roads, one-way streets are like that. And undirected weighted two-way streets, like if I need to get from, or just cities, like if I want to go from one city to another, I have a road and that road goes in both directions. Like I could go, we could take 74 east to Peoria, and then from Peoria we could take 74 west to Galesburg. And then the weight would be, either the travel time or the mileage or the amount of gas, like some number that represents the cost of traversing that direction. Oh, hey, look at this. I put some answers. Is in a movie with weighted by number of films. Okay, fine. And yeah, whatever. These are not great examples, but they're examples. Okay, multigraphs. So sometimes it's useful to allow multiple edges between the same nodes. This is called a multigraph, right? So there's more than two ways to get from Galesburg to the Quad Cities, but there's two obvious ways when we want to go get Thai food. So you can either take 74, the interstate, or you can take US 150, which is basically Henderson Street, and you just keep like driving north and it dumps you out right by the airport, and then you make a left and a right, and then look. We go for Thai food a lot. That's what I'm saying. Thai food is really good in the Quad Cities. Anyway, so we would have these two, nodes here, but they would have two edges between them. So the same pair of nodes, but two different edges. And these can have different costs. This one's a little bit longer, but it's faster because it's an interstate. This one's a little bit shorter, but it's a little slower because you go through all these small towns and you've got to go from, 50 miles an hour down to 25 miles an hour. Like the cop in town will pull you over and give you a ticket. And then also, maybe we could measure like the amount of beauty, so like this is a less pretty ride than this is. This goes through, beautiful farm country, but also small little patches of woods. And this is like, it's an interstate. So it like looks like an interstate. It goes through cornfields. So that would be a multigraph if you would allow multiple different edges between the same pairs of nodes. There's also such a thing as a hypergraph. So this would be, the idea here, it's a graph where a single edge can actually connect one or more vertices. So, you can see like here's edge 1, which actually connects, vertex 1, 2, and 3, and then edge 2 just connects vertex 2 and 3. Now, edge 3 can connect these 3 vertices and so on, right? So it's different than a multigraph. A multigraph, you can have multiple edges between the same nodes. A hypergraph is the kind of opposite of that, or the dual of that, where you can have a single edge that connects multiple nodes somehow. I don't really understand applications of hypergraphs. There are applications of hypergraphs. I was kind of looking at it and I was like, you know what? I'm going to go try to learn something else instead. It would be really interesting. Like, I wish I had time. I think this is where, like, if I were like an immortal, like if I were like Duncan MacLeod of the Clan MacLeod and I were a Highlander, like I would probably just like take a few years and learn math. Like I'd probably just do that. Like while I'm sword fight, you're millennials. You're not going to get Highlander references. I don't know why I'm referencing like TV shows from the 90s. God, I need to get a life. So to simplify our lives for this class, we're going to assume graphs are not hypergraphs and they're not multigraphs. And in fact, like in general, in computer science, if somebody says graph, they don't mean hypergraph and they don't mean multigraph. They mean, your questions are going to be, okay, is it directed or undirected? And is it weighted or is it unweighted? That's what graph means for computer science. And if people meant hypergraph or multigraph, they would have said so. Okay. Some other thoughts. So a graph has vertices and edges, or again, networking background, you're going to say nodes and edges. The degree is just the number of edges. So, a cyclic graph has cycles. This is an undirected graph, and it's got cycles. I can go from A to B. I can go from B to D. I can go from D to H. Then I could get back to A, right? So I could take a cycle through this graph. So we would say that graph is cyclic. An acyclic graph, no cycles. So if I start here, right, and assume I don't take backwards edges, so I could just start cruising around. Unless I take a backwards edge, I'm not going to have a cycle. There's no way to have a cycle. And in fact, if this graph were directed, I wouldn't have a cycle, anyway. And typically, even if this is an undirected graph, it still doesn't have a cycle because there's no way without taking a back edge to get back to a node you've already been to. So we'd say that this is acyclic. There's special types of graphs called DAGs, a directed acyclic graph, right? So a tree, all trees are graphs, but they're special graphs. They're DAGs. They're directed acyclic graphs. So I start here. I can go here. I can go here. It's directed and it's acyclic. There's no cycles. There's no edges in a graph that take you from D back up to A. That wouldn't be a graph. That wouldn't be a tree, right? This is a tree. So I can't go here, and then come back up to A. That wouldn't make it a tree. So all trees are DAGs. But it turns out not all DAGs are trees. This is a DAG, but it's not a tree. You can look at this and you're like, well, that doesn't make any sense. I can't have A as the root of the tree, which goes to Z, but then there's this other root over here, and even if these aren't the roots or something like that, you never see this in a graph where you can have one subtree and then jump to the other. You would never really see that. So this is a DAG. It's directed and it's acyclic. There's no cycles. There's no way to get back to B, but it's not a tree, right? So, and this is just to sort of let you know, all trees or graphs, they're just special kinds of graphs. So other terminology, dense, sparse, and complete. A dense graph has a lot of edges relative to the total possible number of edges. So what this means is a lot of the edges are close to their maximum degree. A sparse graph is going to have relatively few edges, right? So that means that most graphs are going to have most nodes are going to have a very low degree. And a complete graph, that's the densest possible graph. It has edges between every possible pair of vertices. So here's a complete graph. This has 1, 2, 3, 4, 5 edges. There's what? What are there? 1, 2, 3, 4, 5, 6, 7. There's 7. So each of these are going to have 6 edges. It's going to have an edge to everything else. So they would say that that's a complete graph. So we got to think about connected versus disconnected. So a graph is connected if there's some path from every node to every other node. And a graph is not connected if there's not. So this is a graph. It has 8 nodes and a bunch of edges, but it's disconnected because if you're in this subgraph, there's no way to get over to this subgraph and vice versa, right? There's no way to jump between these. So we'd say that's a disconnected graph. The complement of a graph just means, you take all the possible, basically whatever edges there are, we would get rid of them. And any place there's not an edge, we would add it. So if over here you see in this graph, there's an edge between A and B. When we take the complement of this graph, there's no edge between A and B. But here, there's no edge between A and D. When we take the complement, now there is an edge between A and D. So we're just toggling. If there's a possible edge, but there isn't one, we put it in there. And if there is an edge, we just get rid of it. So that's the complement of a graph, which is typically written with this little not symbol G, or sometimes G with a bar over it if you're using not Google, which can do that bar at the top better. Moving on. Isomorphic. Oh, wow, formatting here really got screwed up. So two graphs are isomorphic if there's a one-to-one mapping, or also known as a bijection, between them. So these two graphs, you can create a one-to-one mapping here, Oh my God, I'm yawning. I guess node 1 becomes A, and node 2 would become B, and node 6 would become D, and so on. We can create a one-to-one mapping, even though this is drawn differently than this, and the nodes have different labels. We could create a one-to-one mapping and make these the same graph. This is also exactly the same, right? This just depends on how we write it. There's no issue. Graphs don't, unless we restrict the graph further, they don't have any notion of a spatial dimension. So the fact that this looks like a square and this doesn't look like a square, it looks like a weird hourglass thing, and these edges cross each other, that doesn't matter unless you've added additional restrictions to the graph and decided, like, how it sits on a two-dimensional plane really matters. This is actually the same as well. There's no rule that says the edges have to be straight lines. We can so these are all actually the same graph. We've just drawn them differently. So infinite graphs. Most graphs are finite. So that means there's a fixed number of nodes and edges. But it's actually possible to have an infinite graph, a graph where you just sort of keep generating things and it just like goes on forever. So here's a good example. So this is this 8 puzzle game, where you can like slide pieces around. You try to get things into order. So imagine we slide 2 up. Now we slide 2 down. Now we slide 2 up. And we just sort of keep doing that. That's going to go on forever. This is pretty obvious, but if you like slide a bunch of things around, you could eventually get back to this state, this exact state, a bunch of different ways. So in this situation, imagine that each node is the state of a game of an 8 puzzle. And then each edge would represent a different action you can take. So this action would be like sliding 2 up, or another way to think about that is sliding the space down. But there's other actions you can take from here. You could also slide the 3 over, which is also thinking of like sliding the space to the left, and the same with 5. So there's like 3 possible actions you could take, each of which is going to take you to a new node, and that node would then sort of contain the state. So this is something you see in artificial intelligence all the time, and you see it with both sort of one-player games or puzzles, where you're trying to reach some particular goal state by making these actions. You also see it in 2-player games, so things like chess or checkers or Connect 4 or things like that. And so for things like checkers and chess, where you can like move and then sort of move backwards, the board state can repeat, so you have to be a little bit careful about that. So if we don't take steps to prevent revisiting a state we've already seen, we go from here to here. If we allow ourselves to go from here back to here, that's actually it's pretty much the same thing as having an edge that points back up here. So that's not a tree anymore. It's now a graph, but it's not a tree. So typically for AI, we're going to like take some steps to be like, you know what, I've seen this state before, so I'm not going to allow myself to take this move and see that state again. We'd have to do something like that in artificial intelligence. So I mentioned a good way to generate an infinite graph is just sort of generate it programmatically. So chessboard. Oh, God. That'd be another way to do it. Making graphs not infinite in AI is actually really important. AI also has a lot of graphs. They're not infinite, but they are exponential. So the canonical examples, chess, I think the numbers on chess are for any move, for any state, there's on average 30 different relevant moves you could take. And I guess it's like 30, each game tends to have something like, I can't remember, 50 or 80 total ply, which a ply is like a half a move. So if I make a move, that's 1 ply, and then you make a counter move, that's 1 turn of the game, but it's actually 2 ply. Ply is just like how far down this graph. So like, if at each time there's 30 different possible moves starting at the beginning of the game, it's not exactly 30, but that's a good estimate. That's exponential, right? That means that there's 30 states you could go to, then there's 30 squared, then 30 cubed, then 30 to the 4th, and that just sort of, boom, that explodes. So this is why chess is a hard problem to solve with a computer, because, you're searching. It's not infinite, but it's exponentially big. And things that are exponential, when the numbers get big, if you want to search 20 moves ahead and there's 30 moves, that's 30 to the 20th. That's pretty friggin' big, right? That's a very, very large search space for you to search through. You're going to have to take things to make that smaller. So just some stuff to think about. And again, these graphs are not really graphs. They're really going to be trees. But again, a tree is a graph, so who really cares? So a lot of the stuff we learn in using graphs in computer science actually ends up applying to sort of restricted versions of graphs like trees and things like that. But it's just a really good thing to keep in mind. And I think, that's all I have. Let's see how that video went.